So, we have discussed about Fanno flows. They are compressible 1D flows with friction. We looked at how they behave, what are their equations, and we solved a simple numerical in a subsonic case. Let us solve a couple of numericals now. You can also look at what happens in supersonic case and if there are shocks and so on. So, let us look at this problem. A gas, gamma is given 1.3, R is 287. So, please make note of gamma, it is slightly different from what we usually use. So, if you are using calculators, online calculators, then there is an option to change gamma. Okay. So, at P1 equal to 1 bar, T1 equal to 400 Kelvin. So, it is given. So, P1 is given, T1 is given, 400 Kelvin, enters a 30 centimeter diameter duct. Okay, duct diameter is given at a Mach number of 2, M1 is given. So, let us draw the duct. Okay. We know P1 is 1 bar, T1 is 400 Kelvin and M1 is 2.0. A normal shock occurs at a Mach number of 1.5. So, it is a Fanno flow with so in supersonic conditions Mach number decreases. So, at somewhere in the duct, some location, we do not know the location in terms of length, but we know the Mach number. Mach number is 1.5 at which the shock occurs. So, let us call this particular place, okay, I call it as x, and after the shock as y, and what is known is at the exit at location 2 the Mach number is 1. So, here exit Mach number M2 is equal to 1. It is very effective if you are able to draw a TS diagram of this particular case. So, what we are looking at is essentially something of this kind. This is the star point. So, initially you have started with Mach number 2. So, this is point 1 and follows the Fanno curve, reaches a point x where there is a shock. So, the shock transfers the Fanno curve. So, the line that is being followed from x to y, which is located on the subsonic branch of the Fanno curve, and it reaches point 2, which is exactly equal to the star condition. So, it is useful to draw this. If you understand this, then it is once this is understood, it is reasonably easy to calculate all the other things. Friction coefficient, the mean value of friction coefficient is 0.003. So, f prime 0.003. Determine the lengths of upstream duct and downstream duct of the shock wave. So, what is the location of the shock wave? We know the Mach numbers at which they are located. So, this is at 1.5. So, mx equal to 1.5, we know this value. So, and we also need to find the change in entropy, mass flow rate of the gas and so on. So, let us look at this problem. Now, so we know that normal shock, if it is located at M1, so mx is 1.5, then we know my, it is a normal shock, okay, but please make sure that gamma you change, it is 1.3, my is 0.69, okay. Pressure ratio across the shock is Py by Px is 2.413 and Ty by Tx is 1.247, okay, and P0y by P0x is 0.926, and we know M1 it is 2. Okay. So, how do we proceed from here? Okay. So, what we should find out is what is L1. So, at Mach number equal to M1 equal to 2.0, the value of 4 FL star by D, this is known, it is 0.357. You can also make note of P by P star, it is 0.424, T by T star is 0.719, and P naught by P naught star is 1.773. Okay. So, it is better to make note of them, and we know Mx at Mx, this is 1.5. So, 4 FL star by D at 1.5 is 0.156, and P by P star, similarly P by P star is 0.618, T by T star is 0.86, P naught by P naught star is 1.189. Okay. So, what is the length now before the shock? It is easy to find that out. So, 4 FL by D is equal to 0.357 minus 0.156, which is 0.201. So, L is 0.201 multiplied by diameter, it is given 30 centimeters. So, 0.3 divided by 4 multiplied by 0.003, this turns out to be 5.025 meter. Okay. Similarly, now across the shock you know the conditions. Okay. Now, across the shock the condition is that your Mach number is My is 0.69, and 4 FL max by D or FL star by D for 0.69 is 0.2525. So, P by P star is 1.501, T by T star and P naught by P naught star is 1.1048. So, similarly, so downstream it is directly L star. So, we know L star. So, because it is going to Mach number 1 at the exit. So, L2, this is L1, L2 is 6.3125 meters. So, that solves the problem. The second case is what is mass flow rate. For this you need to know the mass flow rate m dot is rho 1 v 1 a 1. A is known because diameter is given 30 centimeters or 0.3 meters. So, area you can find pi by 4 d square, area turns out to be 0.0706 meter square. Density rho 1, P1 and T1 are given. So, you can find out rho 1 is P1 by R T1, okay. That is 0.871 kilogram per meter cube. And what about V1? V1 is Mach number is given 2.0 and multiplied by square root of gamma r T1, okay, where T1 is 400 Kelvin. So, substitute all of them here, put them, and m dot turns out to be 47.515 kilogram per second. Now, how to get net change in entropy delta S by Cp? Okay, so for this we can use or delta S by R. You can use delta S by R. It should be related to the change in entropy. So, is minus log of P naught 2 by P naught 1. So, if you know the total change in P naught 2 by P naught 1, there is change in the or ratio of the stagnation pressures, then we can find out what is the entropy change. Okay. So, so here what are the stagnation changes? If you write P naught 2 by P naught 1, this can be expressed as P naught 2 by P naught y multiplied by P naught y by P naught x multiplied by P naught x by P naught 1, where P naught 2 by P naught y comes from Fanno flow, Fanno curve, or those equations. P naught y by P naught x is normal shock, the stagnation pressure ratio across normal shock, and P 0 x by P naught 1 is again by Fanno curve. Okay, though you can get these by different, you know, Mach numbers at each particular point. So, P naught 2 by P naught y can be expressed as P naught 2 by P 0 star by P naught y by P 0 star, and similarly P naught x by P naught 1 is P 0 x by P 0 star divided by P naught 1 by P 0 star. You can express these all these in terms, and finally you can arrive at P 02 by P 01, and delta S by R is e power minus so delta S by R is directly log of P 02 by P 01, sorry. Okay. So, if you get P 02 by P 01, then delta S by R is equal to 0.576. Okay, that is the change in entropy. Right. So, let us this looks at a problem in which we have a supersonic flow coming in, there is a normal shock in the middle of the duct at some location, and finally at the exit Mach number equal to 1. In these situations always it is useful to draw the TS diagram, and then it is very easy. Once you know the TS diagram, you know what you are looking for, and rest of it is through charts, or you can use the online calculators to get the other numbers. The essential concept one has to understand, okay, the location of shock and how to represent it on a Fanno curve. Now, if you look at the next problem, the stagnation chamber of wind tunnel is connected to a high pressure air reservoir by a long pipe of 100 mm diameter. If the static pressure ratio between the reservoir and the stagnation chamber is 10 and the reservoir static pressure is 1.0135 into 10 power 7 Newton per meter square, how long the pipe be without choking? So, what should be the length of pipe so that there is no choking? Assume adiabatic subsonic one dimensional flow with a friction coefficient of 0.005. So, let us represent it schematically. This is a sort of applied kind of a problem where you are considering wind tunnels, and we had looked at how wind tunnels look like in the previous classes. They usually have air reservoirs which are located quite far away from the test section. So, relevant problem, and they are connected by pipes. So, you have a long pipe, and this is air reservoirs where a large amount of air is stored, okay, air reservoir, and this diameter is given d equal to 100 mm, and here you have a smaller stagnation chamber, okay, it is a smaller stagnation, and then further it goes down, you have the wind tunnel down. So, what is given is the ratio of pressures across this. Now, if you consider reservoirs, what you would say as static pressure, inside the reservoir the velocities are going to be extremely small. So, the you can almost take that P naught is approximately equal to P. So, if this is 1 and this is 2, then what you are essentially given here is P naught 1 is approximately equal to P 1 and P naught 2 is very close to P 2 inside the reservoir or inside the stagnation chamber, somewhere at this location you can say. But please mind that at the entry to the pipe and the exit to the pipe you can have different different static pressures, because flow will obviously be coming in, gushing in from all directions. Similarly, flow will be exiting over here. Okay. So, they are not talking about these entry points here, which is 1 and 2 for the pipe. What we look for is 1 and 2 of the pipe, but what you are given of course is about what is there inside the reservoir. Okay. So, can we now look at this problem. So, what we are given is basically P naught 2 by P naught 1 or P naught 1 by P naught 2 is given, the ratio is 10. Okay. And what about now we are considering that what should be the length that it does not choke. So, the what is the maximum limit? Maximum limit L max is the point when it chokes. So, m equal to 1. Suppose we take the maximum limit, that is L max, m equal to 1. Any length which is less than L max will satisfy that it is not choked. So, we take the limiting condition L max is, so this is equal to L max. So, L max. So, what do we know about that? We know that it is P by P 1 by P star. Okay, this is what is known, P 1 by P star. This can be written as P 1 by P 0 1 multiplied by P 0 2 P 0 1 by P 0 2 multiplied by P 0 2 by P star, or P 2, or P 2 is actually P star in this case. Okay. This is equal to this, and P 0 1 by P 0 2 is given. Okay. And also we know that at 2 Mach number m 2 is equal to 1. Therefore, P 0 2 by P 2 is also known at that particular point. So, this is P 1 by P 0 1 multiplied by 10 multiplied by 1.893. Okay, 1.893 should be equal to P 1 by P star. What is P 1 by P 0 1? This is 1 by 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1 multiplied by 18.93. And what is P 1 by P star? This is from Fanno flow, this is across the pipe, that is 1 by m 1 multiplied by gamma plus 1 by 2 divided by 1 plus gamma minus 1 by 2 m square the whole power 1 by 2. Okay. So, this is what we know from Fanno flow. Okay. So, now we have an equation solely in terms of gamma and m Mach number, which is m1 here, where gamma is equal to 1.4. Okay. We can further take m1 this parameter over here, and you will get this as 1 by m1 multiplied by gamma plus 1 by 2 multiplied by 1 plus gamma minus 1 by 2 m1 square whole power 1 by 2 gamma minus 1, okay, equal to 18.93. Okay. This is known for us. This is also a constant, you can divide that. So, you will get 1 plus m1 1 by m1 multiplied by 1 plus 0.2 m1 square divided by 1, this is 2.5, sorry, raised to 2.5 is equal to 17.2806. Now, we know that Mach number is extremely small. Okay. So, for a so this of course you have to solve, but it needs an iterative solution. But one fact we know, Mach number is extremely small at the entry. So, m1 square is going to be very small. So, if we take that approximation, then this parameter is going to be 1. So, Mach number m1 will approximately be equal to 0.057868. So, we get a ballpark number. This is a number where the Mach number of at 0.1, and we can then look at iterating this slightly. So as to satisfy even more closer this particular condition. Okay. So, you can do a little bit of iteration, and exact number is very close to 0.05957965. So, you see if you take the third decimal place, they are almost the same, 0.058, because this is 0.058. So, this is known. So, once you know this, you know that L star, that is L star you can get by finding out what is 4FL star by D for this Mach number. This is turns out to be 207.14. Therefore, L star is 1035.69 meters. So, any length which is smaller than this L star will not have a choked flow. So, this is a nice applied problem where pressure ratio was given across the reservoirs, and then the length was the maximum length at which choking would occur is taken. Okay. So, there are two problems. So, we have covered a problem in subsonic flow, a problem involving supersonic flow and shocks, and an applied problem. And this covers Fanno flow, which is one of the driving changes of compressible flow in ducts. So, we have discussed two drivers, one is variable area, the other one is flow with friction. Now, one more driver is flow where there is heat transfer. When you consider heat transfer, you do not consider varying area or friction. That kind of a flow is known as Rayleigh flow, which we will see in the next class. Thank you.